good morning, everyone. So my name's Tom Zonizer. This is Keith Kirkendall, and we're both with Intel and part of the HPC field team at Intel. So we focus on all HPC products, which specifically are Xeon Phi, fabrics, software, and storage. So we're going to go through kind of a high-level overview today of some of these products in terms of the products and capabilities that we offer today, as well as what's coming tomorrow. Obviously, there's a lot more material that we can share with you. So if you have specific questions, we're at the table in the other room, or we can set up a follow-up call to drill down into some of these technologies if you have an interest. Additionally, there'll be some things that are NDA that we're not permitted to talk about today, but we absolutely can share that information with you moving forward if you have an interest. So we'll skip over the legal disclaimer stuff and jump right in. So, as I mentioned, the HPC products at Intel kind of sit in 5 different pillars. And Intel is very focused on high-performance computing products. We recognize that this is a growing market, year over year, and at the same time, if we can meet the strong demands in the HPC community, that can benefit other market verticals as well. So if you wanted to talk back about a year and a half, Intel was at International Supercomputing, and they kind of drew a line in the sand, and they said, we're going to deploy an exascale system by the end of the decade. And at the same time, they took a look back, and they thought, all right, well, what are the potential challenges that could interfere or prevent us from being able to be successful in deploying an exascale system? So clearly, there's a lot of CPU and flop power that's required, but at the same time, energy is a big concern. Right now, there's no way that you'd be able to power an exascale system with the technology that's available today. Additionally, parallelism and vectorism is the way of the future. So it's really important for the ecosystem to begin to parallelize their apps. And as they're modifying those applications, they're vectorizing them and making it multi-threaded so that they can scale across a large number of cores. Additionally, there's storage concerns from a file system perspective. So we need to make sure that we can meet the data-intensive requirements that the HPC community requires. And lastly, to tie all this stuff together, fabrics are necessary. So if we look at this chart here, I think you guys are all pretty familiar with Xeon processors. We've been a leader in the community for a number of years. And earlier this year, we released the first generation of our Xeon Phi many-core processor. So Keith will tell you more about what that capability is, but effectively, as we're parallelizing codes now, we want them to run on many cores, and this is going to be a low-power device that will be the wave of the future. From a software perspective, we have Intel MPI, we have Intel compilers, we have different libraries, but at the same time, we offer Intel Cluster Studio and Intel Parallel Studio to help with this porting and this parallelization process so that people can understand where hotspots exist within a code and where memory leaks may exist so that they can be resolved and these things can be rolled out to a large cluster. From a storage perspective, we do have solid-state drives. We also have something called cache acceleration software where you can really optimize hot parts of memory by leveraging cache acceleration. But additionally, last year, Intel made an acquisition of WAM Cloud. And WAM Cloud was one of the key contributors to open source Lustre. So now we own that IP, and we continue to develop that IP. And as we develop it, we release this stuff back into the open source community. And lastly, from a fabric perspective, last year Intel made 2 acquisitions. They acquired the InfiniBand assets from QLogic, and they acquired the interconnect assets from Cray. And now those folks are sitting in a room and effectively they're coming out with our next generation fabric technology. So we're not really able to talk too much about that today, but if you do have an interest, we can set up a follow-up call and we can go into the details of what that architecture looks like and how it's really going to revolutionize and change fabric capabilities, moving forward through the end of the decade. From a top 500 perspective, on the top left here, you can see, since '06, the blue bars represent, the market segment share that Intel Xeon has played in the top 500. In terms of the most recent release of the June top 500 list, we have 81% of the systems deployed, and 98% of the new listings are using Intel Xeon processors. So, Sandy Bridge processors are really performing well, and now we're on the cusp of launching the Ivy Bridge, which actually is being launched this week. Also, for the first time since 1998, Intel has the #1 end-to-end system on the top 500. So it's known as the Milky Way system, or Milky Way 2 in China. It's 34 petaflops. It's over 3 million cores. And you can see that it's using 32,000 Ivy Bridge processors and 48,000 Xeon Phi processors. So this system here actually is twice the performance of the #2 system on the list, which is pretty rare. That you don't often see that. Additionally, you can think of this system 34 petaflops, and we're talking about exascale by the end of the decade. We have to basically do 30x the performance to create an exascale system. At the same time, this Milky Way 2 system, the power envelope is about 18 megawatts, and our expectation is that we need to do exascale computing in a 20 megawatt envelope. So effectively, we've got to do 30x performance with no additional power in the next 7 years. And now I'm going to turn it over to Keith, and he's going to go through some of our processors.
All right, so we at Intel love three-letter acronyms, and I'm from Texas, so we kind of have our own vocabulary way of speaking. So if I say something you don't understand, please stop me, and I'll interpret it back into standard American English. Are you guys familiar with Intel's TikTok manufacturing and processor development strategy? A little bit. So basically what Intel does, every year, we either release to the market a new technology or a new processor microarchitecture. The reason Intel does this is basically to minimize risk in our development process, but also to try to deliver maximum value to the industry. So what we do is everything that's called a taco here is a new microarchitecture. Everything that's called a tip is actually a shrink of the previous microarchitecture. So this was called Marone, Penryn, the Nehalem, Westmere, Sandy Bridge. Ivy Bridge is the latest generation of Xeon processors that we're launching this week in Intel Developer Forum in the Bay Area. And we've actually released Haswell 4 2 cores in the client. Next year we'll do Haswell 2 and 4 socket servers, 2 core and 8 socket servers and above as well. Talk through. All right, so the current Xeon E5 2600 processor that we're shipping right now, the code name inside Intel was Jaketown. But if you look at the current Dell servers, HP servers, or servers from any vendor, the majority of them are based on this platform. It's a 2-socket platform. Each socket has 4 memory channels for up to 24 DIMMs in a single 2-socket. We've got 40 lanes of PCI Express Gen 3 per socket, 2 QPI links for basically snoop and cross sockets, I/O and memory traffic. It's an 8-core processor. The new 8-core processor built on 32 nanometer technology. The new Ivy Bridge drop-in processor is up to a 12-core CPU. It's 2 threads a core. Each core has up to 2.5 megs of cache, so a 12-core will have 30 megs of cache. And it's built on 22 nanometer technology. What's cool about 22 nanometer technology, I don't know if you guys keep up with it, geeky transistor stuff, but we actually build what are called FinFET 3D transistors now. And what that means is instead of being a planar transistor, we actually build the gates thicker so that you physically have more room for electrons to flow through the silicon. That means that you can turn transistors off and on faster, you can turn them off and on harder. And one key benefit of this is they switch faster, but they also leak less. So when you turn them off, you have less wasted power on the die. So these processors are more efficient. You also, because of the transistor shrink, you get more cores in the same area. So we deliver value to the market by giving you, 2 extra cores at basically the same price at higher performance and similar frequency. Because this is a shrink and not a new micro architecture, the technology differences from an instruction set architecture perspective are pretty small. We do have a new instruction that HPC guys are interested in called Float 16. It's basically a data type conversion instruction that if you're using 16-bit floating points, gives you more effective bandwidth on the processor. We also do virtualized APICs, and that's useful for people doing virtualization. And we have a digital random number generator. So we got a couple of op amps that sit there, and the voltages just float around. We got some circuits that'll grab the voltage and translate that into a hash and a random number. So there's no good way to create an attack based on timing or something of the circuits. All right, so have folks here heard of Xeon Phi? No? You ever heard of Larrabee? All right, so back in the day, a couple years ago, Intel tried to get into, we looked at doing high-performance graphics on general-purpose cores. We called it Larrabee. It was a big mini-core die. Well, what we found out was graphics software is pretty hard, and the way to make graphics software easier is to do it on dedicated, designed for graphics hardware. So we gave up on that. However, what we found in that experiment was that it was a pretty good flops throughput machine. So we took that graphics processor, invested about $3 billion over the last 3 years, and created a new coprocessor microarchitecture called Xeon Phi. The current generation of Xeon Phi was codenamed Knight's Corner. It's built on 32 nanometers. It's up to 61 cores. Each of these cores is actually based on the old P54C first Pentium core. So we took that core and put in a bunch of the later generation technology. So we duplicated a bunch of resources to add hyper-threading. So we've got four threads per core. We also bolted on a very large vector throughput unit to the cores. So Knight's Corner can do about a teraflop of double precision floating points sustained. And we demoed that last year at IDF. It was running LinPack at a sustained teraflop per card. So the differences between Xeon and Xeon Phi. Why would you choose a Xeon Phi over a standard Xeon or even over a GPU, right? Xeon Phi is really good if your code is really, really parallel. So if you have more than 20 or 30 threads and the data set fits inside, a certain bandwidth and memory profile, Xeon Phi is an incredible throughput machine. If your particular application doesn't scale past 20, 25, 30 threads, you probably are better off on regular Xeon. Yeah, shoot.
You mentioned it has 61 cores. You must be doing something with another 3.
No. Wow. It's a weird number. Yeah. Not every. So we've got 3 different lines. There's a 7100, 5100, and a 3100 line. As a manufacturing strategy, we do die recovery stuff, right? So we can test if we have cores that don't work, we turn them off, things like that. So 61 is just, when you're building silicon, you've got a reticle limit size, like how big you can physically make a die. That's just how much you can fit on the die. All right, so Xeon Phi. If you look at this performance chart, right, over here is code that's not highly threaded and not vectorized. Where we see tons of benefit on Xeon Phi is in this corner, where the code either has lots and lots and lots of vectors. Think of things like seismic processing, protein folding, life sciences genomic sequencing, some manufacturing flows, things of that nature. Xeon Phi does really well on. However, what we found, I don't know if we have a slide there, we don't. And what we found, right, is if your code is what we call embarrassingly parallel, then you can get some really incredible speed ups with Xeon Phi. The other nice thing about Xeon Phi, too, you get speed ups using like a GPU or more fixed function hardware. Nice thing about Xeon Phi is it uses our standard programming tools. So you use Intel compilers, you use Intel Fortran libraries and math kernel libraries, our code profiling tools, VTune and things of that nature, run on Xeon Phi as well. And if you do the work to thread, parallelize, and vectorize the code, what we see is, just take this molecular dynamics thing, right? We see up to 2.5 times better throughput on Phi than we see on Xeon. However, a lot of the work to make the code run faster on Xeon Phi actually makes it run a whole heck of a lot faster on Xeon too. So if you see, like the NVIDIA guys will say, we see 300% speed ups. Well, it's because they're talking about unoptimized single-threaded code versus highly optimized, parallelized, threaded, and vectorized code. Right? What we see is if you do all the work to get the most benefit and go back and run it on a Xeon, there's, on very, very highly threaded code, maybe a 10x speed up is possible. All right, so Xeon Phi, we'll talk about what makes Xeon Phi really different with a GPU for a second. I talked about the tools that you use, right? It runs standard x86 code, but it's actually its own computer on a node. It runs its own Linux-based OS. You can program it like it's a supercomputer in a box. You use regular MPI programming, you use sockets if you like. It does a lot of things that make it a very flexible solution. Right? You can run the entire program on Xeon Phi, or part of it on Xeon, part you can offload to Phi. You can do it the opposite way too, where you run the main program on Phi and offload single-threaded parts back on the Xeon. So it's a flexible solution. The other interesting thing, right, if you look at this solution on the right, you realize that you can take a Xeon Phi out and set it aside and have a standalone computer, right? So our future roadmap, we've got something called Knight's Landing. We talked about this as supercomputer. Will actually be a standalone, socketable part with its own memory system. So you won't need to put it with a Xeon if you don't want to. We'll also have code processor add-in versions as well. We talked about all this, didn't we? So you guys ever use Intel software tools? Compilers, things of that nature, libraries? So Intel's got a large investment in software tools. Right? So we've got compilers, we've got optimized libraries for crypto, math, SOAR, hashing, things like that. But we also have these tools that are useful for code profiling. And I won't read this whole list to you, but if you look at like VTune, right? So load the code, load VTune. As you run the code, VTune will do performance profiling of the code as it runs and point out hotspots and will suggest to you optimizations that you could make to improve the throughput of the code. We also have Intel Advisor XE actually will help you thread the code correctly. It'll point out problems with spin locks and things of that nature. True scale. Let's talk about true scale.
So we talked about the fact that Intel made a couple acquisitions last year on the fabric side of the house. The InfiniBand products continue to be sold and supported today. So these are, we refer to it as TrueScale Fabric, and effectively we have QDR40 and QDR80 solutions available. So we have the host channel adapter, which is the PCI Express adapter that sits in the host. There's a variety of form factors depending on the solution that's being deployed. And then we also have the switch silicon, which is embedded into 36 port 1U switches all the way up to our largest director is 648 port non-blocking, or we have an 864 port if you have 2-to-1 oversubscribed. So basically we're an end-to-end service provider here, providing all the software capabilities. We qualify third-party cables, so you don't have to buy proprietary cables from us. We have host heaven manager. However, we fully embrace OFED as well, so if you want to use OpenSM, that's fine. And then we have management tools, which we call Intel Fabric Suite, which helps with large deployments. So a few years ago, the DOE labs, Lawrence Livermore National Lab, Sandia National Lab, and Los Alamos National Lab basically made a decision about a project called TLCC2, which was 20,000 Sandy Bridge nodes that they were going to deploy. And there was a bake-off between TrueScale and Mellanox's PCI Gen 3 technology. And they actually found that TrueScale performs and scales better than our competitor. So that's what's been deployed. And what we found is, there are so many applications today that they're not bandwidth sensitive. They're really latency sensitive and they're message rate sensitive. And that's the differentiator between our capabilities and what our competitors deploy. And this is also going to be the foundation of our next generation fabric solution that we brought to market. In addition, I mentioned Lustre. So, Intel acquired WAM Cloud a year ago, and basically the blue box here represents the number of lines of codes changed by each of these contributing companies. So WAM Cloud / Intel, makes the lion's share of the changes to Lustre. In addition, WAM Cloud and Intel were awarded the Fast Forward award from a storage perspective for a large opportunity that's in the 2017 timeframe. And there are a lot of requirements from a feature and capability perspective that need to be integrated. So again, this is part of Intel's investment into high performance computing to ensure that it meets the needs of the community moving forward. So today, Intel, we fully embrace Lustre from an open source perspective. We're also coming out with an Intel Enterprise Lustre solution. There's also an Intel Manager for Lustre that's available for ease of installation, configuration monitoring, and then we have a professional services group that can provide training, whether it's admin training or overview classes. They'll also do professional services if issues exist with your Lustre file system and you need help troubleshooting. And we do provide level 3 support for many of the storage vendors that are deploying Lustre solutions today. And that's what we had prepared to share with you guys. Any questions?